to wrap up this series of videos in section 15.4 on our polar coordinate stuff, I want to just explore a little bit about where does the factor of r come from. And I'm going to give two explanations for this. One explanation is going to be here in this video. The second explanation won't come until section 15.8. But let me offer the first explanation here of where do we come up with the r. So here is my answer, is that I want to consider a small change in r and theta. How does that change area? So the picture that I'm going to draw here, okay, so I'm going to assume right now that we have some fixed value. Okay, let's see here. Okay, so right now we're at this like r theta point, and I want to make a small increase in theta, and I want to make a small increase in r, and I want to see how much extra area do I get from this. So I'm going to increase theta just a little bit. This looks like a pretty big increase in theta, but you know, I'm drawing it big so that we can see what's going on here. And then I'm going to increase r just a little bit. So that right there is our change in r. And then we've acquired this new area right here. This is like the change in our area. Okay, so the question is, how does this change in area relate to the change in r and the change in theta? So in order to answer this question, we need to recall a high school geometry fact, which is if we have a circle of radius r and we want to find a sector that sector of the circle with angle theta, the area here is 1/2 times r squared times theta. I'll just point out to you a little quick justification of this formula is if you take theta equal to 2 pi into this formula, you get 1/2 times r squared times 2 pi is pi r squared. Theta is equal to 2 pi is the entire circle. What's the area of the entire circle? Pi r squared. So this checks out. Okay, so back over here, we need to calculate the area of this little region. We're going to do that by finding the area of this entire region here, and then subtract off the area of this smaller region here, and the difference will be the change in area. So this area, the small, this smaller one right here, the angle here is delta theta, so our area here will be 1/2 times the angle, as I said, was delta theta, and the r distance there is just r squared. So the area of this region is 1/2 r squared times delta theta. How about the area of the bigger region? So not just that down there, but that with the orange region up there. Okay, well, it's going to be 1/2 times the angle here is still delta theta, and the radius here is r plus delta r. So 1/2 times r plus delta r, quantity squared, times delta theta. So then to find the area, to find delta A here, it's the big area minus the small area. I mean, not that this is that small, because that will be a lot smaller. We should be thinking of this as, you know, kind of small here. So 1/2 times r plus delta r squared, delta theta minus 1/2 r squared delta theta. Okay, so let's crunch this out. We want to expand out this product here. 1/2 times r squared plus 2r delta r plus delta r squared times delta theta minus 1/2 r squared delta theta. And both of these terms here have 1/2 delta theta in them. So let's factor that out. 1/2 delta theta times r squared plus 2r delta r plus delta r squared minus r squared. Hey, look, those r squares get canceled out. And so we are left with 1/2 delta theta plus 2r delta r plus delta r squared. I can factor out another factor of delta r here. 1/2 delta r delta theta times 2r plus delta r. Now, we're thinking of delta r and delta theta as very tiny, infinitesimally small objects here, you know, or more formally speaking, we're taking the limit as these go to 0. So we're going to take the limit as this goes to 0 here, you know, compared to 2r, this is essentially nothing. So we get rid of this term. So now I put an approximation here. 1/2 delta r delta theta times 2r, 1/2 and 2 cancel out, r delta theta is about delta A. So delta A is about r times delta theta. In the limit, we're taking out all this infinitesimally small, and we replace these with the differentials. dA is equal to r dr d theta. And so that's why when we're doing an integral in polar coordinates, dA gets replaced with r dr d theta. So this is one explanation for where does the r come from. This is one explanation. We'll see another explanation that's a more general explanation in section 15.8.